because I gave you guys a reprieve from the warm-up so that you could spend your time hopefully studying, um, the very first bit obviously doesn't quite work. So grab grab something that's straight, like a ruler if you've got one, or just the edge of a piece of paper. And what we want to kind of just demonstrate here is, so we've got the graph of 2 to the x, which, not surprisingly, it's kind of this number, okay? And what I want you to do is, there are 5 x coordinates there, so maybe just pick one of them kind of at random. Um, and I want you to draw the tangent line to the curve at that point. Okay, so sketch it on the grid, and then using the grid lines, give me an estimate of the slope. Okay, now this isn't going to be perfect, obviously, because you guys will just be estimating, but it'll be good enough to kind of illustrate the point. So -2, -1, 0, 1, and 2. So like I said, just pick one randomly, and then that way we can kind of speed through this a little bit. Okay, so what did you guys get? Who did -2? Nobody did -2. 0.2. Okay, -1. Bueller. All right, let's start at the other end. Who did 2? Who did 1? All right, what'd you get? 1? Yeah. Okay, that one was kind of easy. What about at um, well, we'll come back to this. 0. Who did 0? Because what you're telling me is a bunch of you just sat your asses there and did nothing. I got that right? Come on, wake up, guys. All right. What'd you get at -1? Like maybe a half-ish? And at 0, huh? What'd you get at 0? Slightly less than 1. All right, well, how could we figure this out exactly? Well, what does the limit definition say? Well, let me just do this at, say, 0 as a, for sake of example, but we could compute this limit, okay, and kind of see what we get. Now, there's a problem. We don't know, like, when we were doing the analytic limit stuff before, where we had like our conjugate trick and common denominator tricks and all of that sort of stuff, none of those tricks are going to apply here, right? So there's nothing we can do to simplify this to let us do it algebraically. And so if we want to sort of estimate it, then all we can do is use very, very small values of h, okay, and plug in and get an idea. So if I were to do, for example, 2 to the 0.1, like that, this would give me a ballpark estimate. And then if I did it with 0.01, then I'd get a much better estimate, right? Okay, so we kind of have to go back to that trick. All right, so for the sake of computation's sake, let me just do this real quick. All right, so I want to do, I'm just doing this real quick in Mathematica. And I get 0.717 blah, blah, blah. Okay, that seems reasonable? Yeah. Okay, and we could do this for certainly the other points too and use better values of h, but I'll just skip forward to the sort of result. The derivative of 2 to the x is 2 to the x times the natural log of 2. Okay, now let's check this against what we just did. If I plug 0 into this, what do I get? Right, so let's say I did this at 0, and I plug 0 into 2 to the x times log 2. What do I get? What's anything to the 0? 1. Okay, so I just get log 2. All right, so what is the natural log of 2? Well, okay, so we don't necessarily know exactly what it is. But first off, can we suss out if it should be a positive or negative quantity? Probably positive. Can we suss out if it's a number bigger or smaller than 1? It's actually going to be a little bit smaller. Okay, here's why. Natural log of what is equal to 1? Natural log. E, right? In the same way that the log of 10 is 1, right? So if the natural log of E is 1, what is E roughly? 2.7 something, right? If we're taking the natural log of 2, well, 2 is less than 2.7, and so we should expect that it'll be less than 1, and it is. It's like 0.693147, blah, blah, blah. Okay, so is our 0.71 really that horrible of an estimate from before? It's a little overdone, but pretty close. Okay, so the big result then is that if we have any base, then all you have to do is pop out a natural log of the base. Okay, and in particular, the one that we're going to use a lot is this. Okay, if the base is e, well, what's e to the x times the natural log of e? Yeah, because what's the natural log of e? We just said it was 1, right? Okay, so this is yet another reason why e to the x and the number e itself is so interesting, okay? Because e to the x has the property that it is its own derivative. That's really interesting. By the way, there's only one other function that has that property, that is its own derivative, and the other one's not nearly as interesting. Any guesses as to what it is? 0. 0 also is its own derivative, but that's not a very exciting function, is it? Yeah. So, yes, sir. What do you mean? Oh, 2 to the h? Oh, so if my function was 2 to the x, right, what's the limit definition? And I'm going to do this specifically at 0 just for sake of demonstration. Well, f of 0 plus h, but what was the function? 2 to the something, right? Oh, yeah. That's bad. Okay. Shouldn't misplug in. Okay, so does that kind of make sense? Yeah. All right, so now that we have this result, this will be super handy, okay? And on the same token, we could also do this kind of game for trig functions. So we'll do that next. Huh? Oh, no, trigonometry is beautiful. Okay, so what is the tangent, or the derivative of sine of x? All right, well, first off, we need to make a good sketch of sine of x. And for that, let me just flop over to Desmos. Where did my keyboard go? There we go. Okay, so if I sort of zoom in on this, I'm going to concentrate my attention on what's going on between 0 and 2 pi, because, of course, the thing just repeats anyway. Well, looking at this, what do we notice in terms of our slopes? Well, what's the slope here at 0? Looks like it's roughly 1. What's the slope at pi over 2, which would be here? 0. What's the slope here at pi? Minus 1. What's the slope here at 3 pi over 2? And what's the slope up here at 2 pi? Looks like it's plus 1. Okay, so do we know a function that if you plug in 0, you get 1, and when you plug in pi halves, you get 0? Cosine has that property, okay? So in fact, let me graph cosine along with it. Okay, and now let's see if this whole thing holds. What is the slope? So let's pick a different point, like let's say here. What's the slope there roughly look like? Yeah, slightly less than 1, but it happens to be exactly the value of the cosine function at that point. Okay, so the limit, the derivative of sine is cosine. Yeah? Ah, that's kind of cool. How could we maybe prove this? Huh? Somebody else already did. Fair point. Fair point. That's how math works, right? Well, we'd have to go back to the limit definition, right? Doesn't sound fun? Oh, come on, it'll be fine. All right, so I want to know what's the limit as h goes to 0 of f of x plus h that, right? That's what I'd have to figure out. Well, what are we to do? Because there's no conjugate trick or any other garbage that we could maybe use. Well, okay, we could approximate this at a point if we plugged in a specific x and a very small value for h, right? But that's not good enough. So we go back to, you guys happen to remember that identity? If anybody does, then you need to like see a professional because you shouldn't remember that. I should have these memorized, but I don't. Huh? All right, so it's sine A cos B plus cos A sine B. Yeah, you guys remember those? Yeah, that's basically what we'd have to do here, right? Um, so we'd have to say, okay, limit h goes to 0 of, all right, so what would this be? Sine x cos h plus cos x sine h minus sine x all over h. Okay. Just trust Sir Isaac? Yeah, what do you guys think? Yeah. All right. So yeah, to take this further, it's not that hard. Basically, what we have to do is, you guys remember when we had the limit of sine of x over x as x went to 0, right? And a similar one for cosine. We have to break this up to look like that. Yeah. So let me actually just, we're not that far off, right? Now that we've got it here. So what I'm going to do is I'm going to put sine of h over h times cosine of x. And then I'm going to do plus sine of x times cos of h minus 1 all over h. Okay, and I'm going to put the limit out front of this one too. So I just split it into two terms. Okay. Now, what is this limit, and why can I ignore the cosine part when I'm computing that limit? Right, it has the cos x attached to it, but why can I ignore that temporarily? Because what am I taking the limit as? What does what? H goes to 0. Are there any h's in cos x? No. So it's basically like a constant right now. Right? Now, the limit in the red box, do we remember the value? It was 1. Okay, this is one of those special limits that I told you guys had to take on faith. Right? It's 1. So this part is just cos x. And then this limit was the other one, and that one turned out to be 0. It came from right here, because I factored the sine x out because both of the remaining terms had 1. So, yeah. And I didn't flub anything else, did I? Hopefully not. Okay, so that's it. There's the proof. Okay, now, this does depend on the fact that what were the limit of the red and the green boxes? 0 and 1, or sorry, 1 and 0 respectively. And how did we know that? I told you to take it on faith. Well, I still haven't proved those. Okay, so technically, we're still not like ironclad here, but yeah. Okay. So similarly, it turns out that the derivative of cosine is minus sine. Okay, and you can prove that one kind of similarly. You just have to look up the other trig identity. And so what's neat here is that if you take the derivative of sine or cosine, it goes in a circle. That's maybe not surprising. And every 4 derivatives, you get back exactly where you started. Okay, so the derivative of sine is cosine. The derivative of cosine is minus sine. Well, what's the derivative of sine? So what's the derivative of minus sine? And then what's the derivative of cosine? Minus sine. And then if it's minus cosine, it'll be sine because you'll have double negatives. And so just around the circle you'll go. Okay, is that good? Okay, so we got derivatives of sine and cosine, and we got derivatives of the exponential functions. Okay, we got one other, which is the logarithm. It turns out to just be this. Okay, so the derivative of natural log of x is 1 over x. Okay? Good? Huh? Well, it's a function, right? Because there's still an x in it. Yeah. Yeah, that's always true. Okay, so let's use these, right? So let's look at numbers 3 and 4 here on our sheet. So everybody on that half of the room do number 3. Everybody on this half of the room do number 4. And if you could be so kind as to utilize a board, then once you've got it figured out, then you can write it. Somebody can write it up on the board. Yeah, look at that, Jaden. All right. Huh? Yeah, you get your half has 4. Okay. And wake up. It's not that early. But the sun is above the horizon. Have any of you guys been paying attention to where the sun rises every day? Oh. It's not east. It's only east on 2 days of the year. It's a little bit south of east. And the amount that it's south of east is decreasing every day by a little bit until late March, in which case it'll be due east. And then for the next half of the year, it'll be a little bit north of east, hitting its maximum deviation from east on June 21st, which is the summer solstice. Yes, it's called spherical trigonometry, and I actually do teach a class on it. No, you don't. You won't. It's actually really, really awesome. Well, okay. So let me give you guys just a quick little taste of this. What's Pythagoras' theorem? On a sphere, that's Pythagoras' theorem. No, but that's the equivalent of Pythagoras' theorem. So if you have a right spherical triangle and A, B, and C are its side angles. So this is the fun thing about a sphere, right? On a sphere, the sides actually are also measurable by angles because an arc along a sphere you can measure by the angle at the center. So sides are also angles, which means you can take sine and cosine of them. Yeah, of course. Yeah. It's awesome stuff, man. And now you might ask, when in life are you ever going to use that? Right? Well, let's say I dropped you on a boat in the middle of the ocean, and all I gave you was a clock, a sextant, a slide rule, a bunch of paper, and a book of numbers.
Clock and a what?
Slide rule and a sextant. I have one in my office. It's a device for measuring the angle from the horizon to a celestial object. So it's like a fancy protractor that has like imagine if a telescope and a protractor had a baby, you'd get a sextant. Right? So you hold it up and then you look through it and then you move it until you get the thing and then you read off the angle. So, all right. So we got any results going on here? All right. Looks like it. Jaden, number 3. So what you got there, bro? Okay. Almost completed equations. What's missing? And where do we get the y value from? Yeah, you just plug in pi halves to the original function. So it'd be 4 in this case. Yeah, because what's sine of pi over 2? 1. Yeah, there we go. Okay, so what do we got? Well, what's the derivative of 4 sine of x? 4 cosine of x, right? And how do we know that the 4 just kind of stuck around? Well, the constant multiple rule that we talked about last time. All right, so we need we've got the derivative. What do we need to write the equation of a line down? Point and slope. Okay, so how do we get the point? Well, we know the x-coordinate, that was given as pi halves. So where's the y-coordinate come from? The original function, right? So if we plug pi halves into sine of x, or 4 sine of x, well, what's sine of pi halves? 1, and therefore 4 sine of pi halves is 4. Okay, so the y value is 4, so that's why we got y minus 4 at the beginning there. Okay, good. Now, what about the slope? Well, where do we get the slope from? Yeah, plug the x value into the derivative. So this time we're doing 4 cos of pi halves. Well, what's cosine of pi halves? 0. Okay, and so what's the slope in this case? 0. So we just have the horizontal line. Okay, good. And now what's probably the two mistakes that you could make on these things? One is botching the derivative. Okay, that makes sense. But probably the easier mistake to make is, where do you get y coordinates? The original function. Where do you get slopes? Don't mix them up, right? Because obviously if you get those backwards, then if you pizza when you should have French fried, you're going to have a bad time. No? Of that? It's the when they all go to, it's in South Park, right? When they all go to the ski resort and their parents get trapped in like the timeshare presentations forever, and the kids get to go skiing, and their instructor, who's of course his name is Chad, is like, that skiing is all about French fries or pizza, right? To speed up or slow down. So, yeah. Ah, 4 cosine of pi halves equals 0, right? So what do we need to plug in? So first off, do we agree that the derivative is 4 cos x? Okay. The x coordinate that was given was pi halves. So I need to plug that in. And then what is cosine of pi halves? And those we have dutifully memorized, right? Uh-huh. There is a table. Yeah, you remember the old unit circle? Huh? Please don't. What do you mean? Well, it's about to cause you some more pain. Huh? It should be in here. Because, yeah, of course. Yeah, you got to know your unit circle, bro. Huh? Yeah, well, that ship sailed when you showed up at Wabash. Okay. I mean, now there is an alleged university to the south where I bet you they do give you the unit circle tables. Yes, right. No, seriously, you guys got to know your unit circle. Um, so, uh, yeah, I'd start making some flashcards or something. So, none of you guys had to memorize unit circles in high school? You forgot all of them, of course, right? Yeah, no, you just gotta know those things, guys. I'm sorry, but I'm not a huge fan of blatant memorization of things because I was never particularly good at that in school myself. But there are some things you just have to sit your ass down and memorize, okay? And the unit circle is one of them. It's kind of like, do you know your multiplication tables? Of course you know your multiplication tables. Huh? Well, so is the trig functions, right? So is the unit circle. Just a more interesting pattern, right? But like the unit circle is the multiplication tables for college. There's a red cup right there. Oh, do you want me to fill it up with beer? A little early for that. I don't know. We could go to Nuevo Kentucky Cafe and have enchiladas. Whiskey Club? Oh, well. So here's my line on student clubs. I judge everything as being either more or less ridiculous than Cigar and Pipe Club. right? That's the line. If it's less ridiculous than Cigar and Pipe Club, it can be a thing. So anyway, yeah, that's my yeah, but I doubt they're using college money to buy crypto. Right? But Cigar and Pipe Club does buy tobacco with student senate money. So yeah, so they are literally smoking your tuition dollars. Yeah. Yeah. Huh? Barbecue club? Now see that's good, right? Yeah. And if you want a really different kind of smoking, you go over to Phi Psi. Oh, I mean, so all right. Good. What about number 4? Find tangent line to f of x equals e to the x at x equals 0. Well, what do we have to do first? And what is the derivative? Happens to be exactly the same thing. Okay, that's nice. And if I want to do a tangent line at x equals 0, I need to plug in 0 and I get 1, right? Because e to the 0 is 1. And what about the slope? It's also 1. Yeah, y minus 1 equals 1 times x minus 0, or y equals x plus 1 if I move everybody over to the other side. Okay? Now, what do we want to do here? I want to approximate the value of e to the 0.1. So I know that f of 0.1 is going to be approximately, so let me call this this thing L of x for tangent line. Okay? If I plug 0.1 into that, am I going to get the exact value of f of 0.1? No. But is it going to be close? Yeah, reasonably. Okay. And of course, it's really easy to plug 0.1 into that function. What do I get? 1.1. Okay, so that was easy. Right. Now, let's compare this to what, well, what e of 0.1 actually is. So the true value using my fancy calculator is about 1.10517 dot dot dot. Okay, so it's pretty good, right? Um, and this is something that we did last time, right? If I want to approximate a function, I can use this tangent line to do it instead, provided that I'm pretty close to the point of tangency. Okay, if I'm really far away, then I'm going to get just absolute garbage. But if I'm pretty close, so like if I did this with 5, right, I would get 6. E to the 5 is a hell of a lot bigger than 6. But pretty close to 0, which is the point at which I constructed this tangent line, this is not all that horrible. Okay, and which one's easier to compute? Plugging things into this linear function or plugging things into something that's not linear? Well, clearly the linear function's easier to work with, right? Um, okay, good? Yeah? All right, so let's flip over. Because, well, now the rules start to get fun. Okay? And in particular, what would happen if we had two functions that we knew individually what their derivatives are, but they were multiplied together? Okay, so let me just start with kind of a deliberately cheesy example. What's the derivative of x to the 4th? 4x cubed. Okay, done. Right? No big deal. But let me rewrite x to the 4th and let's think about it in a different way. if I thought about this as x squared times x squared, what I'm basically asking here is what's the derivative of the product of two functions? Well, wouldn't it be nice if it was just the product of the derivatives? That would be nice, but we cannot have nice things. It's not just that. Okay, and in fact, we can see why it can't be that thing. If I did that, what's the derivative of x squared? What's the derivative of the other x squared? What's 2x times 2x? But what are we supposed to get? So that doesn't work. Huh? Well, because it's wrong, I guess, right? Okay, so do you guys see what I'm trying to get at here? If I tried, okay, so let me just write this as, well, let's go into the bullshit zone. Yes. Okay, so that's the bullshit zone. So if we came into this thinking, oh, the derivative of a product should just be the product of the derivatives, seems like a perfectly reasonable first guess. Does it work? No, because we get an answer here for this example that doesn't match with what we should have gotten. Okay, so do you guys see that? See the point I'm trying to make here? Okay, so if it's not the product of the derivatives, what is it? It's something more complicated, which I'll write down in a second. Okay, but it's not that. Okay, now this is a little irritating because when we did limits, what was the limit of a product? That was the product of the limits, but it doesn't hold for derivatives. Okay, is that annoying? Yeah, well, this is why we have math classes, right? Because, like, if all of this was easy and obvious, we wouldn't be here. You guys would all know it already. So, yeah. Julius, is this going to cause you more pain? Well, okay, what don't you understand, right? Like, if you don't understand something, then ask a question. Well, that's what we're going to get to. We haven't done that yet, right? So it's not just the product of the derivatives, okay? Unfortunately, yes. Yeah, there's a rule for it, appropriately called the product rule, okay? And that's what we're going to write down. Okay, so what it turns out to be, I'm trying to take the derivative of two functions multiplied together. And it turns out to be this. It turns out to be that I do one of them times the derivative of the other, and there are two possible ways I could do that, so I do both of them and add that up. Okay, now, would you have necessarily guessed that it was going to be this? Probably not. What do you mean? Ah, okay, good question. Yes and no. Okay, by which I mean, so let's say that one of the problems is I give you two functions and I say, use the product rule to get the derivative. There, I would deliberately want you to not FOIL things out at the end, okay, and simplify. Because let's say that, well, like, let's look at this first example, and I'll illustrate what I mean here, okay? So look at number 5 on the sheet there, right? I've got two horrible looking polynomials, right? And I'm defining their product to be h of x. So the derivative of that is the first thing times the derivative of the second thing. What's the derivative of the second thing? 5 plus 16x minus 3x squared. Let me make a little bit more room there. Okay, plus I need to do the first thing's derivative. What is that? Okay, times the second thing, which I just copy down. Okay, so what is everything? This is f, this is g prime, this is f prime, and this is g. Okay, so do you see how I pieced everything together based on our rule? Oui ou non? Okay, so Mark's question is, what should we do here? Could we FOIL all that crap out? We could. Don't. Okay, unless we're then trying to do something extra with it. Well, okay, for a tangent line, I wouldn't, because if I were trying to do a tangent line, I'd be plugging a number into this, and it might actually be easier to, like, let's say I plugged in 0, then a lot of these terms are going to disappear, right? So, yeah, but like later there'll be a point where we'll set this thing equal to 0 and solve for x's that make that happen. In that case, then it would be good for us to go ahead and simplify, because it'll make the algebra that comes later easier to get our hands on. Okay, so yeah, so good question. So for the standard stuff, that if you got to something like this, I would rather you not simplify it. Okay, for multiple reasons. One, do you really want to simplify that? I mean, you could, right? It would kind of suck. But two, let's say that you go through and you start simplifying it and you botch that part. Well, if I look at your answer, am I going to know if it's because you botched the calculus or because you botched the algebra? It won't be immediately obvious. Okay. And so, in terms of sussing out, do you understand the calculus? If you leave it unsimplified, then that makes it really easy for me to tell, did you get the calculus part right? So my assumption is that you guys, if I gave you a few minutes, could all correctly simplify this thing, right? It would suck. It'd be a mess. But if I gave you 20 minutes and said just go and started cracking the whip app on my phone, you'd be able to get it, right? Okay, so like that's high school shit. We're not here to do that. We're here to do calculus because we're men. Damn it. Yeah. Okay. Right. So that's the product rule. All right. So, uh, any questions about this example or the statement of the product rule? Good. Well, if we can do products, what else could we do? We can do quotients, right? They're kind of the same idea. And the quotient rule is a little nastier. All right, so if I've got one function over the bottom, it's going to be the bottom function times the derivative of the top function minus the top function times the derivative of the bottom function all over the bottom function squared. And here's maybe an easy way to remember it. You're trying to take the derivative of high over low, right? So it's low-d high minus high-d low all over low squared. Okay, now, here's your real test to see how cultured you guys are. Does low-d high, high-d low, does that remind you of any songs? Yeah, Cab Calloway, Minnie the Moocher. Hidey, 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 high. Hidey, hidey, hidey. Loady, loady. You guys know that song? You don't know Minnie the Moocher? Oh, no. It's like Harlem Renaissance jazz, like from the 20s. Yeah. Yeah, it's an old song, but No? You don't know jazz history? Well, that's okay. I had to teach my retro computing class how to read sheet music the other day. That was like liberal arts college moment, like big time, because here it is, they're in the 300 level CS class, and I'm like, let's learn how to read sheet music. Only half of them had read sheet music before. Not all of them even had done it ever. It was a little surprising, I will admit, but yeah, I know, right? So, how many of you guys can read sheet music? Okay, maybe not play it correctly, but like you can at least read the sheet music itself. All right, how many of you have never read sheet music in your entire life? How many of you, the only music that you've ever done is in fourth grade when you had to play the stupid recorder, right? Yeah. Do they still do that in schools these days? Yeah. You didn't? Oh. Ah. Well, way to toot the horn there. Yeah. So, okay. So let's apply this, right? Now, there's one point here. What happens if you get the order on the top backwards? It's going to be, you'll get the negative of the answer you should have gotten. Okay. If you get the order wrong in the product rule, it actually doesn't matter because it's a plus, right? But if you get the order wrong in the quotient rule, it's not going to work. Okay, so just be really careful, and this is why the low-d high thing maybe is helpful. Okay, to keep that uh, firmly implanted in your brains. We okay. So let's apply this to a problem. Well, if we can do, well, actually, this should be enough room. Well, what's the derivative of tangent? Well, let's figure that out. Yeah, what is tangent of x? It's sine of x over cosine x, right? Okay, so now this is written in the form of a quotient, and so we can apply the quotient rule. All right, so the low thing is cosine x. Um, what's the derivative of the top thing? Also cosine x. Okay, and I will simplify this one, but later. Okay, minus the derivative of, or sorry, the top thing, sine, times the derivative of the bottom thing, which is negative sine, all over the bottom thing squared. Okay, yes, sir. No. Okay, but if you wrote cos of x squared with no parentheses, then I would interpret that as that the x was being squared, not the whole function. Okay. All right, so let's simplify this. Okay, so the double negatives cancel in the top, so I've got cos squared plus sine squared all over cos squared. Look good so far? Does anybody happen to remember what cos squared plus sine squared always is? 1. You're jumping ahead of yourself there, Jaden. Sine squared plus cosine squared is always equal to 1. Okay, now how do I know that? That actually is Pythagoras' theorem, right? Because if you draw a unit circle, what are sine and cosine? They're the coordinates of a point on the circle. And so sine squared plus cosine squared is the square of the radius, but what is the radius in a unit circle? 1. So 1, okay? Now, cosine squared in the bottom, we got that. What's another name for division by cosine? So 1 over cosine, we give it a separate name. It's secant. And so this one is secant squared. Okay. Now, you could leave it as 1 over cosine squared. That's fine. But I think in practice, it's it's easier to work with secant because now there's no fraction. Okay. And also, if you look things up in books, this is what you'll tend to see. So, yeah. Okay. Gucci? Yes, sir. Yes, good point. Okay, so do we have to do the quotient rule every time? Not unless I explicitly tell you to. Okay. Okay, since we're out of time, what are you guys doing today? Yeah, sleeping. Yeah. And the exam. So I have a really full calendar today. So right outside my office door, there's a little wood box that's bolted to the wall. Inside the yellow folder, you will find your exams. And because now we're at the point where everybody has to do different pieces, get out the one that has your name on it. Do it on separate paper, staple everything together, and then put it back in the blue folder when you're done, right? You don't even have to see me about it, okay? All right, see you guys later.